Okay, so.
It just came back on.
Okay. You've been presented as the manager of a department store. And you've been told that you have to get rid of one salesperson. And what you've decided is you've got it narrowed down to 2 people, and you've decided that whoever has the worst week next week is the salesperson that you're going to get rid of. So, you've got it narrowed down to Pat and Chris. And this week, Pat sells $1,200 and Chris sells $2,700. But you realize that that's not necessarily fair because they are in different departments and certain things are easier to sell than others. So you decide to compare them to their own department. In Pat's department, which is toys, the mean sales is $2,000 with a standard deviation of 250. In Chris's department, which is electronics, mean sales are $3,400 with a standard deviation of 200. So in order to make this fair, we have to compare their standard or their z-scores for their sales rather than their flat out sales numbers. So for Pat, how do we find Pat's z-score? Perfect. So it's 1,200 minus 2,000 divided by 250, which is going to give us negative 800 over 250, which is a negative what? 3.2. How about for Chris? Perfect. 2,700 minus 3,400 divided by the standard deviation of 200. 27 minus 34 is negative 700 divided by 200 is negative 3.5. Who's going out the door? Chris is gone. Okay. So you can see how this z-score is kind of a handy little tool when you have spots where you have to compare things that aren't necessarily from the starting out on equal footing, put it that way at least. Okay, so our next step. Z-score is kind of it uses the mean and standard deviations. It's kind of what we call a measure of position. Now another measure of position that we're more familiar with is something called a percentile. What a percentile is, technically, is it's telling us where you are compared again to other items in the same data set. And technically, the way the percentiles work is they're saying what percent of the people or what percent of items in this data set are below the value or less than the value that you are looking at. So what we're going to start off with is we're going to start off with a set of data. Now, just like with a median or some other things, it's important that the data is put in order from smallest to largest. So we're going to start out with a set of numbers that's smallest to largest. So 17, 24, 28, 29, 30, 32, 33, 33, 36, what do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. There. So we have a list of numbers. And let's say we are asked to find the 75th percentile. Now, one thing I'm going to do is I'm going to start off by numbering these right away. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It does two things. One, I need to know what n is, and n is 12 because there are 12 of them. So that's one thing from the start that's going to help me with. Two is to find these percentiles, I'm going to have to be able to quickly find locations in the data, so having them numbered is going to help me with that too. So we put them in order from smallest to largest, just like with the median. Also, just like the median, we're going to have to find a position. The position, though, is going to be based off the percentile times n. 75% is what is a decimal? 0.75. Times n is 12. What's 0.75 times 12? It's going to be 9. Now with the median, if that came out to be an exact number, a whole number like that, what did we do with it? It was between that one and the next one. What this is telling us is that our 75th percentile is between the 9th and 10th number in the list. Now, if you're using Excel or some other electronic, some of the electronic data organizers have an algorithm to figure out how far between 36 and 39 that this is. We're just going to do just like we did with the median. We're going to add them together and divide. So the 9th number is 36. 10th number is 39. We're going to add them together and divide by 2. Gives us 37.5. Is the 75th percentile. So if I ask you to find the 30th percentile, what am I going to do to find the position? Yeah, 30% is 0.30 times 12 is still n. Gives us 3.6. Now for the mean, or for the median, I should say, if that came out to be a decimal, what did we do? We round up. The number in the 4th position is the 30th percentile. That's going to be the 29. So 29 is the 30th percentile. In your notes, I want you to find the 85th percentile, and I want you to find the 25th percentile. So for the 85th percentile, how do we find the position? .85 times 12, which gives us what? 10.2. So the number is in the 85th percentile is in what position? The 11th number, which is, yes, so 39 is the, oops, sorry, 40 is the 11th number. Whenever it's a decimal, even if it's 10.1, it rounds up to 11. 25th? Oh, yep. Always round it up, yep. If it's a decimal. Now for the 25th percentile, what do we do? 0.25 times 12, which gives us what? 3. What's that tell us about our position? It's between 3rd and 4th. So it's between 28 and 29. 28 plus 29 divided by 2 is 28.5. Any questions on that part of it? I just copied my list of numbers just to make it a little easier to do the next part so I don't have to scroll up and down. So now if I am asked to find a number that is in a certain percent, or find what percentile a certain number is in, I should say. So let's say I'm asked to find what percentile, oops, come here. What percentile is 36? Now, we may have found earlier that 36 was a certain percentile. I think we did find it. Oh, no, we didn't. The 36, though, is in the 9th position. Now, the thing is that there are, with a small set of data like this, when you find like a certain percentile, the 36 is actually in a range of percentiles. Like the 29, or what was the last one? 28.5. The 28.5 would actually be, oh, that's only for one. So let's talking myself in circles here. I got a little hamster back on the wheel. The 28.5 is between them, so that the 25th percentile is the only one that will give us the 28.5. Like the 26th percentile, that would be the 29, right? But in fact, anything on up to, well, what's it going to be? Like 35th percentile? The 34th percentile, 0.34 times 12 is what? That is 40.8 or 4.08, isn't it? So it's actually be the 33rd percentile. The 33rd percentile would be 0.33 times 12 is 3.99. So the 29 here is actually the 26th through the 33rd percentile. Does that make any sense? If you had to find the 26th percentile, you're going to get 29. If you had to find the 33rd percentile, you're going to get 29. That's because there's only 12 numbers in this list. So each number in the list covers a 7 or 8 percentile range. Because you take 100% divided by 12, that's 8.33. So when you have a small set of numbers like this, it's not a real exact find. I mean, like I said, if I asked you to find the 26th percentile, the 28th percentile, or the 33rd percentile, they're all going to give you 29. Just be aware as you get to larger sets of numbers, for example, more than 100 numbers in the list, well, then it's going to be a lot more useful because there's only going to be one number in each percentile. But anyway, here we are being asked, what percentile is the 36 in? To find the percentile, the percentile is equal to the number of numbers that are smaller plus the number that's equal divided by 2. In other words, half the number that's equal divided by the total number, or n if you wanted to put n down there. So if I look in this list, I'm going to number them again quick just for ease. How many numbers in this list are smaller than 36? 8. Plus, how many are equal to 36? Only the 1. So that's 1 divided by 2, remember, because it's number equal divided by 2. How many total are there? 12. So this is 8.5 or 8.5 divided by 12. 0.708. Now, first thing I got to do is move the decimal point 2 spots to make it a percent. That'd be 70.8. And I'm going to round it up to the nearest whole percent. So that is the 71st percentile. So the 36 is the 71st percentile. So what if I ask you what percentile is the 30 in? Talk me through it. Well, how many is number smaller? There's 4 smaller, yes, plus 1 that's equal, so 1 over 2 over 12. Perfect. So that's going to be 4.5 or 4.5 over 12, which is what? .375, which is 37.5 or 38th percentile. So 30 is the 38th percentile. What if I asked for 33? What percentile the 33 is in? Talk me through it. Okay, perfect. There are 6 that are smaller. Here's the 33, but there's 2 33s. Plus 2 over 2, because there's 2 that are equal to it, divided by 12. So 6 plus 2 over 2 is 1, so that's 7 over 12, otherwise known as 0.583, which is going to be 58.3 or the 58th percentile. What do you think? Bless you. Good stuff? Okay, I'll take that as a yes. Yeah, apparently I just missed it. So, in your notes, I want you to find the 60th percentile. I want you to find the 35th percentile. I would like you to find the 40th percentile. And I'd like you to find what percentile the 17 is and what percentile the 9 is. So try those in your notes quick. So to find the 60th percentile, I'm going to again go back and number them just to make it easier. So how do we find the 60th percentile? 0.60 times 7 is 4.2, which tells us that the 5th number, so 11, is the 60th percentile. Questions on that? 35th percentile, tell me what to do. .35 times 7, which is 2.45, which tells us the 3rd number in the list, which is 9. 40th percentile, what do we do? 0.40 times 7 is 2.8, which tells us still the third number in the list, or the 9. So there again, you can see that 35th percentile and the 40th percentile were the same number. They both came out to be the third number in the list. Again, that's because this is a relatively small list. Once you get over 100 numbers in your list, then you won't have that problem anymore. What percentile is the 17? Tell me what to do. Okay, there's 5 that are smaller, plus 1 over 2, because there's 1 that's equal, over 7. So that's 5.5 over 7, which is going to give us 0.7857142.9 approximately, right? Left out my 4. Correct? Sure? Okay. Which, of course, is going to be the 79th percentile. How many of you got the 79th? Any questions on how we did that? How many just forgot to divide by 2 on the equals? A few of you. Okay. What percentile is the 9? What am I going to do there? How many are smaller? 2 plus 2 over 2, because there's 2 equal, over 7. So that's 2 plus 2 over 2 is 3 over 7, otherwise known as 0.4285714.3 approximately, which is the 43rd percentile. What do you think? I'm seeing the full signs flashing across the foreheads a little early today. So, another measure of position. There's a good reason why I did percentiles first, by the way. How would I find the 50th percentile? Well, the position would just be 0.5 times n, right? That corresponds to our median. The median is just the 50th percentile of any set of numbers. Well, there's some other very significant percentiles that we use. The 25th percentile and the 75th percentile. Along with our median are called quartiles. Quart means what? Quarter or 4, right? Now you look at this, there's only 3 of them. Why does it say quartiles when there's only 3 of them? Well, it cuts the data into 4 pieces, into 4 quarters. And if you have just like a piece of string or whatever, how many cuts do you have to make to cut it into 4 pieces? Only 3 cuts. So it only takes 3 cuts to cut the data into 4 pieces. So there's only 3 of these divisions to cut it into quarters. So there's only 3 quartiles. So the 25th percentile is called the first quartile, or sometimes called the lower quartile. And the 75th percentile is called the third quartile, or sometimes called the upper quartile. And of course, the median is called the second quartile, or sometimes just called the median. These numbers are significant because they divide the data, like I said, into 4 pieces. Now, the size of those pieces is not necessarily the same, but the number of data points in each of those pieces will be the same. For example, let me give you a set of numbers here. What are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's a set of numbers there. I want to find the first quartile, the median, and the third quartile. So my first quartile, 0.25 times, what's n here? Should be the amount of numbers, so it should be 12, right? So 0.25 times 12 gives me 3. So it's telling me my first quartile is between the third and the fourth. Well, the third and the fourth are 11 and 12. So 11 plus 12 divided by 2 is 11.5. How about for my median? Tell me what to do. .5 or 0.50 times 12 is 6. So that's telling me what about my position? Yep, we got it between 6th and 7th. So that's going to be, yep, 14 and 15. So that's 14.5. For the third quartile, what am I going to do? .75 times 12 is 9, so that's going to be between the 9th and the 10th, yep. So yeah, it's going to be, come on, 20 plus 24 over 2 is 22. So we have those quartiles. Now what we're going to do is we're going to make a number line here. Our number line is going to start with our smallest number. And go up to at least our largest number. And what we're going to do is we're going to put some markings on here. The smallest number is 5, so I'm going to put just a mark above the 5. Notice what I did is I just made like a little vertical line, a little short vertical line above the 5. My first quartile is 11.5, so at 11.5 I'm going to make another little mark, again a short little vertical line. My median is at 14.5. Bless you. My third quartile is at 22, and my largest number is at 36. What I'm going to make here is what we call a box plot. Sometimes called a box and whisker plot. So what we're going to do is we're going to connect the first quartile and the third quartile like this to make a box between them. Notice the median sitting in there and somewhere in that box. Then we're going to draw whiskers out to the smallest number and the largest number. Now what this does is this divides our data into 4 sections. This is my first quarter, my second quarter, my third quarter, and my fourth quarter. And what this shows us is where the numbers are tightest together and where they're the most spread apart. Looking at this box plot, can you tell me where you would think the numbers would be tightest together? Quarter 1, 2, 3, or 4? 2. Why do you say 2? Yeah, it's the smallest. Remember, they all contain the same number of data points. They all contain 1/4 of the data points. That one is the smallest, which means the data points have to be closest together. They fit in the smallest area. Let's put those points on here. We've got 5, 9, 11, 12, 12, 14, 15, 18, 20, 24, 29, and 36. And you can see very clearly here, right here is where they are the tightest together. Right here, that's the biggest of the quarters. That's where they're the furthest spread apart. Does that make sense? So I'm going to give you a different set of data right now. We're going to start with the same number. We're going to end with the same number, and there's 12 data points in here. Now, as you might guess, the box plot for this data set is going to be different because they're spread out differently. Let's take a look at that. Let's find the first quartile, second quartile, first quartile, the median, and the third quartile. Do that in your notes for me. The first quartile is where? 11.5, right? You guys get that far? So I'm going to put that up here at 11.5. Of course, the first number, the lowest number is at 5. Where's the median? You get 19.5 for the median? Yes, no? Am I totally crazy? Not really, not there yet? Okay, I'll pause for a minute, let you guys catch up. So then our third quartile is at what? 28.5? And then of course our largest number is at 36. So this gives us a box plot, if I can draw straight lines, which apparently I can't today. It looks something like that. That is about the ugliest box I have ever drawn. What's that? Okay, so looking at the green box plot compared to the blue one up above, what can we say about those numbers? Each section is approximately the same size, isn't it? So they're probably pretty evenly just spread out. Let's take a look. We've got 5, 7, 10, 13, 15, 18, 21, 25, 27, 30, 32, and 36. Those are pretty evenly spread out, aren't they? So by the shape of this box plot, you can tell how the data is grouped. When you get into heavy statistical analysis, the shape of this box plot is a key tool to comparing sets of data. and it can tell you a lot. Now, we talked about outliers before. Outliers, we talked about, I'll have to put the R on the end. When we're talking about mean and standard deviation, an outlier that was anything that was smaller than the mean minus 3 standard deviations, right? Or anything that was larger than the mean plus 3 standard deviations. On that bell curve, it was anything outside of that 3 standard deviations in each direction. Well, on our box plot, our box and whisker plot, there are some other things that can come into play. There's a measure of spread in the box and whisker plot that can be used to analyze our data a little bit more. We talked about the range. For both sets of data here, the range is 36 minus 5, or 31. But then there's something called the interquartile range. What the interquartile range is it is simply the third quartile, I'm going to say Q3, minus the first quartile, Q1. So for our top set up there in blue, that would be 22 minus 12, or 11.5. 22 minus 11.5. It's going to give us 10.5 as our interquartile range. In green, that'd be 28.5 minus 11.5. Or 17 is our interquartile range. When we analyze these, and this is not this, what I'm going to talk about right now is something beyond what I'm going to expect you to know for this course. If you analyze these, comparing the interquartile range to the overall range tells us a little bit about how the data is distributed. If the data was evenly spaced like this, how would we expect the two of them to compare? If they're perfectly evenly spaced, we'd expect the interquartile range to be exactly 1/2 of the range. Make sense? Because the inner two quartiles is the inner half of the data. Now here, for our first set of data, for the blue set, the interquartile range was less than half. What that means the points got a little closer together in the middle. If you look at it, that makes sense, because the points are definitely closer together towards the middle of our data here. They're more spread out on the sides. For our second one here, the 17 is slightly more than half, which means half would be, 15.5 to 16. 17 is a little more than that. That means it's relatively evenly spread out, but it might actually be slightly more spread, or slightly tighter together out on the ends. Like I said, I don't expect you to do that analysis, but what I want to do is this. I want to match you to this. Let's say I have a range of 18 and an interquartile range of 6. That's one set of data. I have a second set of data that also has a range of 18 and an interquartile range of 14. And I have a third set of data that also has a range of 18. An interquartile range of 9. So let's say I do my number line, and I graph my points, and they come out to look like that. Which of those three would I expect that to be? A, B, or C? They're perfectly evenly spaced like that. Well, let's do another one. Let's draw them all out so you can match. Why not? So there, I've got all three sets of data graphed, shown. One of these has an interquartile range that's exactly half the range. This top one, you say is C. Yeah, if the interquartile range is exactly half the range, the point should be almost exactly evenly spread out. One of them looks like this. Now, if you look at here, the points are concentrated in the middle. They're tighter together in the middle. Which one would I expect that to be? A, where the interquartile range is smaller, that means there's more numbers packed together in the middle. That half the numbers are in a smaller section in the middle. And then this one, of course, is C, where the interquartile, oops, sorry, not C. Can't use C twice, can I? This one, of course, is B, where the interquartile range is way more than half, where that means the data points are concentrated on the outside edges. Again, this is more than what I'm going to ask you to know for in this class, but it's kind of a huge data analysis tool. Something like this, you'd be looking at a box plot shaped pretty much like this. All four quarters are about the same. For this, you're looking at a box plot like this, where the center is smaller than the whiskers. And for a box plot here, you're looking at something like this, where the center is large and the whiskers are short. Remember, the interquartile range goes from here to here on each of them. Does that make any sense? Like I said, this won't pop up on a test or quiz, but it's huge for data analysis. If you get into business even, any sort of decision making or managerial position in business, you need to be able to read data plots like that and make decisions based off of them. If you go on to a 4-year degree, by the way, pretty much any 4-year degree you would go on to would have a statistics class in it, and you'd talk a lot more about this stuff. With that, there's a quiz due tonight at 11:59 p.m. and a new homework due for Monday. We're a little early today, but you are welcome to stay in the computer labs and work and ask questions if you want to. Otherwise, you have a great weekend.